Today in this video we are going to discuss about Fermi Dirac distribution function. So what do you mean by distribution function? The distribution function gives you the probability of finding a particle at a particular electronic state or energy state. And the distribution function is a generalization of the ideas of discrete probability where the energy is treated as a continuous variable. So basically we have three different types of distribution function. If we'll start with, we have first is Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution function, which we have already used in kinetic theory of gases. Like we have already used this in molecular velocity distribution. This Maxwell-Boltzmann distribution is applicable in the scenario where you got the particles are identical and they are distinguishable in the sense in kinetic theory of gases we have already discussed, we have already taken that the first molecule is having velocity v1, second molecule is having velocity v2, like n number of molecules you have, and all these n number of molecules will have different velocities v1, v2 up to vn. So in that sense the particles are distinguishable. Then n number of particles can have the same energy. So this is your Maxwell-Boltzmann distribution function. And then we have the Bose-Einstein statistics or Bose-Einstein distribution function. Bose-Einstein distribution function. Bose-Einstein distribution function is applicable for bosons. All bosons will follow this statistics, this Bose-Einstein distribution. And again, when the particles are identical and indistinguishable, particles are indistinguishable, so you will apply this Bose-Einstein distribution function in this case. And then we have Fermi Dirac statistics, Fermi Dirac distribution, Fermi Dirac distribution function. Fermi Dirac distribution function is applicable for all fermions, including electrons and holes. So fermions, and this is applicable to particles which are identical and indistinguishable having half integer spin. Here in bosons you have integer spin, bosons are having integer spin, and here it is half integer spin, so fermions. So to all those fermions, okay, which are identical, indistinguishable and having half integer spin, we will apply this Fermi Dirac distribution function. Now our objective is to find out the electron concentration and hole concentration in the conduction band and valence band. In the previous video we derived what is the density of states in the conduction band and valence band. What do you mean by density of states in the conduction band and valence band? We found what are the number of electronic states present per unit energy range, per unit volume. So that by knowing the distribution function of electrons and holes, and just by multiplying the density of states in the conduction band, that is the number of electronic states available in the conduction band, multiplied with how the electrons will be distributed or the distribution function of electron, you will be able to find out what many electrons will be there in the conduction band. The same way, by knowing the density of states or the electronic states available for holes in the valence band, and just by multiplying it with the a distribution function of holes, you will be able to find out the concentration of holes in the valence band. So that is our objective. So today we are going to see the mathematical form of the Fermi Dirac distribution function, and then we will use this distribution function to find out the concentration of electrons and holes in the conduction band and valence band respectively. So to do that, I will just write the mathematical form of the Fermi Dirac distribution function that we are going to use, and we will study the nature of the function. So the Fermi Dirac distribution function is mathematically given as this is 1 divided by 1 plus exponential of E minus EF divided by KT. So this Fermi Dirac distribution function gives you the probability of finding the electron in an electronic state E with reference to your EF, which is the Fermi energy level, and this K is Boltzmann constant, T is absolute temperature. So Fermi Dirac distribution function gives you the probability of finding an electron in a particular energy state E. So here if you'll study the distribution function, we can just analyze it in different way. Let's take an electronic state E which is greater than EF, the Fermi energy level, okay, and your absolute temperature T is equal to 0 Kelvin at T equals to 0 Kelvin. Now if I put this, if I consider this scenario where I have considered the electronic state is greater than your Fermi energy level and T is equal to absolute 0 Kelvin, then the Fermi function will be your 1 divided by 1 plus exponential of, this is E greater than EF, so positive value, this is divided by 0 Kelvin, which gives you plus infinite. So we got e to the power infinite, 1 plus e to the power infinite is infinite. So we got 1 divided by infinite, which gives you 0. So the probability of finding the particle in an energy state E greater than EF is 0 at T equals to 0 Kelvin. At T is 0 Kelvin. What do you mean by that? There will be no electron in an energy state E greater than EF at T is equal to 0 Kelvin. So all the electronic state will have a value less than EF, less than the Fermi energy level. So this is one. Then the second case we can say, second scenario, in the second scenario we can write, if E is less than EF, E is less than EF, that is you have considered an electronic state E which is less than the Fermi energy level and T equals to 0 Kelvin. T is 0 Kelvin. In this case, you write what is the Fermi function. So this will be 1 divided by 1 plus exponential of, now you got E is less than EF, so this will be a negative value, this T is 0 Kelvin. So you got minus infinite, e to the power minus infinite is 0. This part is almost 0, so you got 1 by 1, which gives you 1. So what do you mean by that? The Fermi function, the probability of finding the electron in an energy state E at T equals to 0 Kelvin below the Fermi energy level is 1. What do you mean by that? All the electronic states below the Fermi energy level at T equals to 0 Kelvin are filled with electrons. Okay. So the third scenario we can consider, let us now take at T non-zero, as T is greater than 0 Kelvin, any temperature which is not absolute 0, and you have, let's take E equals to EF exactly at the Fermi energy level. You consider an electronic state exactly at Fermi energy level. So if I write mathematically, the distribution function will be 1 divided by 1 plus exponential of E minus EF, E equals to EF you have considered and T is non-zero, so it's a defined value. So we got e to the power 0 exponential 0, which gives you 1 divided by 1 plus 1, that is 1 by 2. So finding the electron at E equals to EF, where this temperature is not 0 Kelvin, is 1 by 2, so 50% probability. So mathematically it gives you 1 by 2, the probability is 1 by 2, which is not actually the case, because we said the Fermi energy level is somewhere in between. We will find the exact position of the Fermi energy level later, but right now we are aware of that the Fermi energy level lies in between the conduction band and valence band, and that energy is not allowed to any electronic state or any electrons to be in that particular energy band, which we said the forbidden energy band. So this is not practically possible. The electrons cannot be there in an electronic state which lies between conduction band and valence band. Now, if you will see the distribution function f of E is given by 1 divided by 1 plus exponential of E minus EF divided by KT. Now this distribution function, Fermi Dirac distribution function, can be considered as Boltzmann distribution function, or considered to be Boltzmann approximation in certain condition. Okay, we will see that, and why we need to consider this Fermi Dirac distribution function, and we will convert it to Boltzmann approximation. Okay, because in the conduction band, we have considered the electrons are almost free. They are bound by the surface potential, they cannot come out, but the electrons behave as if it's a free particle and it can move randomly in the conduction band, can move freely in the conduction band. So in that case it somehow coincides with your gas model, like in kinetic theory of gases we considered that. So if I will put some conditions like here, we can just take if this E minus EF is much larger than the value of KT, E minus EF is much larger than KT, then your E minus EF divided by KT will be much larger than 1, and hence exponential of E minus EF divided by KT will also be much larger than your 1, and hence here in the denominator we can take 1 plus exponential of E minus EF is nearly equal to this exponential of E minus EF by KT, because this exponential of E minus EF by KT is much larger than 1. So we can write Fermi function f of E can now be written as, for this condition E minus EF much larger than KT, can be written as 1 divided by exponential of E minus EF divided by KT, okay, which is now in the form of exponential of minus of E minus EF divided by KT. Now this is reduced to the form of Maxwell-Boltzmann approximation. So this reduced to Maxwell-Boltzmann distribution function. So in the conduction band, when we are treating electrons, when you are considering electrons in the conduction band, we will consider this as the distribution function, and then multiplying it with the density of states for the electrons in the conduction band that we have already derived, and integrating it from the energy range. from the energy range. The lowest energy which is defined in the conduction band is EC, conduction band energy, to some value, let's say E. So I will just multiply this GCE with F of E, considering the Maxwell-Boltzmann approximation. I will be able to find out the electron concentration N0. N0 is the electron concentration. So we have the density of states, that is number of electronic states present per unit volume, per unit energy range, multiplied with the distribution function of electrons integrated over the whole range in the conduction band, that is EC, the lower value to E, some maximum, certain maximum, will give you the number of electrons present per unit volume, which is the concentration of electrons. Okay, so in addition to this, let us now see what is that Maxwell-Boltzmann approximation and Fermi Dirac distribution function, if you will plot it. So we got, in those previous cases, we got f of E is equal to 1 when E is less than EF and T is 0 Kelvin. We got f of E equals to 0 when E is greater than EF and T is 0 Kelvin, and we got f of E is equal to 1 by 2 when E equals to EF and T is non-zero. So now if I will show you the curve for the Fermi Dirac distribution function, then if I will take the energy value here, energy and the probability function, then we got this is the maximum value which we said 1, and then here, and this is E equals to EF, this is the value of EF. So we got the maximum probability, this is for T equals to 0 Kelvin. Now if I will take any value greater than 0, so this is what we got, this is for T equals to 0 Kelvin, and now you consider a greater than 0 Kelvin value, so you got this is E equals to EF, E equals to EF. Now for a value which is T greater than 0 Kelvin, now will be the same amount. Now here you got, so this is EF, the reference energy level. So you got sum of the electrons, the probability of finding the electrons in this particular electronic states, in these states will be 0, and the probability of finding the electrons above EF will increase by the same amount, So the electrons now which are not there below EF will be there above EF at a temperature greater than 0 Kelvin. So now this is the curve, this gives you the Fermi distribution function, at non-zero temperature. Okay, so and here the probability of finding at E equals to EF is your 1 by 2, which is practically not possible because it's the Fermi energy level lies in the forbidden energy gap. Okay, forbidden energy or the band gap. So now if you see this, f of E gives you the probability of finding the electron, finding an electron in an electronic state with energy E or corresponding energy E, then 1 minus f of E will give you the probability of not finding the electron, not finding the electron in that particular state, in that particular electronic state. So this can be used 1 minus f of e, which gives you the probability of not finding the electron in a particular state, will give you the probability of finding the hole in that particular state. So if f of e gives you the distribution function for electron, 1 minus f of e will give you the distribution function for hole. So we have already derived the density of states in the valence band, multiplying with the distribution function of hole, which is 1 minus Fe, integrating it over the energy range, some value lower energy level to maximum energy is valence band, or valence band is EV, let's say. Okay, so we will integrate it in that energy range to find out the concentration of holes in the valence band. Okay, now if I will show you the distribution of electrons and holes, or f of e and 1 minus Fe, so in this they are symmetric. So we got at a certain temperature we have this is F, this is Fe and the same way symmetric, if I will consider, this will give you the distribution of hole, which is 1 minus Fe, which is nothing but the probability of not finding the electron in that particular state. So this is energy and this is your Fe. I have taken Fe and this is 1 minus Fe curve. So they are symmetric. Okay, so now the next is, what is the Maxwell-Boltzmann approximation? So Maxwell-Boltzmann approximation we got, which we will apply for the conduction and valence band. So the Maxwell-Boltzmann approximation we wrote is exponential of minus of E minus EF divided by KT. This is in the form of Maxwell-Boltzmann approximation or Maxwell-Boltzmann distribution function. So now if I will show you both the Fermi Dirac distribution and Maxwell-Boltzmann approximation, Fermi curve it is like this, okay, and the Maxwell-Boltzmann approximation is this. Okay, so part of this curve, okay, for this energy values, okay, and this is your f of e. So this is your Fermi Dirac distribution function and this is the Maxwell-Boltzmann approximation, which we are going to use to find out the electron and hole concentration in the next video. So we will be able to find out the electron and hole concentration just by considering the density of states in the conduction band, then the distribution of electrons, which we got the Fermi Dirac distribution function under the condition E minus EF is much greater than KT. I will show you how that E minus EF is greater than KT in the later videos. So this